Okay, so this is our standard heating curve. You should definitely have this in our notes. This is the heating curve for water. We know it's for water because it has a melting point of 0 degrees Celsius and a boiling point or vaporization point of 100 degrees Celsius. Okay, so these here are your melting point and your boiling point. And anytime you change the substance, all you do is change the number, the value for the melting point or for the boiling point. So for example, if you were using, let's say, nickel, go to our packet. If you're looking at nickel, then you would use the melting point of 650 degrees and a boiling point of 1,450 degrees. Okay, so let's zoom in on our packet a little bit. Alright, and then the heating curve of water, you have it here on your packet as well, but you should have all written it in your notes as well. And this just tells you the heating curve for water, the values that we're going to use, and the different Q equals MC delta T values that we're going to use. Okay, so we're going to go ahead and start on page 1401. Okay, how do we solve problems with increasing temperature when we have to go through multiple sections of our heating curve? So 1401, we want to know how much energy must be added to change the temperature of a sample of 53 grams of water. So we're dealing with water from 56 degrees Celsius to 160. So anytime you have a problem like this, the first thing you're going to do is you're going to sketch your heating curve. Okay, we know phase change 2, phase change 3. That's our solid, our liquid, and our gas. And then each flat line is a phase change. Because we're dealing with water, we know that this occurs at 0 degrees, and we know that this occurs at 100 degrees. The next step you're going to do is you're going to take from 56 degrees to 160 and mark those on your calendar or on your heating curve as well. So we're starting out at 56, which is somewhere between 0 and 100, and we're ending at 160, which is up here above. Okay, it doesn't have to be perfectly to scale. We just want to know which states of matter we're going to go through. So for this particular question, we're going to go through 1, 2, 3, 1, 2, 3 steps of the heating curve. Okay, every time you go from a slope to a flat line or a flat line to a slope, that's a different step or a different checkpoint. So we're going to do solve for the heat of each section on this graph. So for Q1, okay, we're going to call Q1 that first section. Q1, if we look at our heating curve, we are in our liquid phase, right? This is our solid, our liquid, and our gas. So we are in the liquid phase. So if we look here at our more detailed heating curve, we're going to use the equation Q equals MC liquid delta T. And the specific heat of liquid water happens to be 4.18 joules per gram degree Celsius. You can also find this number on the front of your packet. Everything under here. Okay, you have your melting points for all of the substances, your boiling points, and the specific heats for the solid, liquid, and gaseous phases for nickel, axium, and water. Axium is that made-up element that we use in chemistry. Okay, so we go back to our Q1. So we know that for our liquid phase, we have a temperature change, so we're going to use MC delta T. Our mass is 53 grams. Our specific heat for water is 4.18. And our change in temperature is from 56 degrees to the boiling point. So from 56 to boiling, we do final minus initial, so 100 minus 56. Okay, then we're going to solve for Q2. This second section, we have to figure out how much heat it takes to boil the entire 53 gram sample. So our second section is going to be mass times the heat of vaporization. Okay, we know that this section here, if we look at our detailed heating curve, this flat line after a liquid, we're going between a liquid and a gas, so this is vaporization. The heat of vaporization for water is 2,260 joules per gram. There's no temperature change, so we don't have to use a delta T. So we say 53 grams times 2,260 joules per gram. And then last, we have to go through section 3 right here. So for section 3, it's another change in temperature. So we're going to use MC delta T. This time, we're in the gas phase. Okay, you can see we're in the gas phase. So you're going to use the specific heat for gaseous water. And if we look here, the specific heat of gaseous water is 1.7 joules per gram degree Celsius. So we use the same mass, 53 grams. Our specific heat is 1.7 joules per gram degree Celsius. And our change in temperature here is from our boiling point, 100, up to 160. So our final 160 minus 100. Okay. Once we're done, our total, Q total, so the total energy it took to get from here to here, we're just going to add them all up. We do 1 plus Q2 plus Q3. And when we do that, we go to our calculator. 53 times 4.18 times 100 minus 56. So Q1 gives you a total of 9,747.76. Q2 is going to be 53 times 2,260, which gives you a Q2 value of 119,780, and 3 is 53, 1.7 times 60, which gives you 5,406. We're going to add those three things together. Add this plus this plus this. We get a grand total of 134,933.76 joules. Okay, and you go through those same steps with every single problem. Then we're going to flip it over and do 1402. Okay, for 1402, we're going to do question number 2, just to give you a, or 3. We'll just stick with 1. So for this one, actually we'll do a different element. Here we go. Number 3, we're going to do axiom. Okay, so for axiom, we're going to have to flip to the front of our packet and get all of our numbers. So on the front of our packet, here we go, we can see that our made-up element has a melting point of 1,000 degrees, a boiling point of 2,000 degrees. Our specific heats for the solid is 1.5, our liquid is 1.67, and our gas is 0.12. These are all the specific heats. We have our phase change values, so our heat of fusion. Fusion is going from a solid to a liquid and back, and then vaporization is going from a liquid to a gas and back. So for fusion, it's 100, and for vaporization, we have 1,000 joules per gram. Okay, we don't know which ones of these we need yet, but I'm just writing them all down so that we can build our heating curve. Okay. So if we look at question number 3, how much energy is required to change the temperature of a 76 gram sample of Exium from 1,123 to 15? So we're going to draw our heating curve, same shape, solid, phase change, liquid, phase change, gas. Our melting point for Exium, we said was 1,000. Our boiling point was 2,000. Our solid phase has a C of 1.5. Our fusion is 100. Our specific heat of our liquid is 1.67. The specific heat of vaporization is 1,000. And the specific heat of the gas phase is 0.12. Okay, so we are going from 1,123 degrees down to 15. So we have a release of energy here. So 1,123 is right about here, right, between 1,000 and 2,000, and 15 is here somewhere below 1,000. Okay, again, we don't have to be specific. We're just doing this to figure out how many steps we need. So here we have 1, 2, 3 steps. So here again, we're going to do Q1, Q2, and Q3. Okay, so this will be 1, this will be 2, and this will be 3. So we're going from a liquid down to, so we're freezing down to a gas, or to a solid. So Q1, we're in the liquid stage. We have a temperature change, so we're going to use MC delta T. Here we have a phase change. There's no change in temperature during a phase change. So for section 2, we're going to use MC, and this happens to be the heat of fusion. And then section 3, we're going from our melting point or our freezing point and cooling it all the way down to 15 degrees. So we have MC delta T. Okay, so for the first one, this first section, we're in the liquid phase, so we're going to use C liquid. Our mass was 76 grams from our question. Our specific heat of our liquid is 1.67 joules per gram degree Celsius. And our change in temperature was final minus initial. So our final is 1,000 minus our initial, which was 1,123. Our section 2, so that'll give us the heat for this first section. The second section, how much heat are we taking away to get from just starting to freeze to all the way frozen? So to do this, we have to use our 76 grams, and then our heat of fusion is 100, but because we're freezing rather than melting, we have to use negative 100 joules per gram. And then here again, MC delta T, so that gives us the heat required to freeze our sample. And then we're going to cool it even further, so we have to use our 76 grams, our specific heat for our solid phase, which is 1.5, joules per gram degree Celsius. And our change in temperature, final minus initial, which is going to be 15 minus 1,000. Okay, when we plug that into our calculator, we use 76 times 1.67 times negative 123. So Q total is equal to negative 1,500 or 156,111.16 plus, so that's our Q1. Our Q2 is 76 times negative 100, which is negative 7,600, plus our Q3, which is 76 times 1.5 times 15 minus 1,000, which gives us negative 112,290. If we add all of those together, our total energy is negative 135,501.16 joules. And this makes sense because we are losing energy. All right, we're going this way. On our heating curve, we're losing energy, so it's negative.